Hello everyone, I'm Norman Wahlberger and welcome to the Algebraic Calculus. In today's video we are going to be looking at log and exp on a central conic. And the topic has to do with an important family, actually families of functions that play an important role in first year calculus. We're talking about the circular functions, the hyperbolic functions, and the log and exponential functions. And what I want to do today is to give you an overview of a kind of unified way of thinking about all these three different families. But a lot of the development of this view will have to wait to the Algebraic Calculus Two course because it's actually very challenging setting these things up correctly. Now, the role of these things is demonstrated very clearly by having a look at a calculator. So here's a modern calculator, and you won't be able to see, but you'll know that prominently here in terms of functions, we have buttons like sine and cosine, tan, log, ln, hype. And these buttons allow us to access these functions as numerical values. So for example, if I turn this thing on and I want to know what, say, sine of 5 is, sine of 5 equals, I find that sine of 5 is 0.08715574275. And that's more than enough precision for almost any conceivable applied mathematics computation or calculation. But from a theoretical point of view, there's still a big gap between this quantity that's exhibited by the calculator and the supposed infinite decimal that the pure mathematician thinks about when he's talking about sine of 5. And the same holds for all the other functions as well. So in fact, from my point of view, the theory of these functions has not actually been established logically correctly. It's a kind of a vacuum where we are going to step in and say what's really going on. And we're going to try to do that by avoiding any kind of reliance on infinite arithmetic and the corresponding symbolics, where we just use things like sine of 5 instead of actually addressing the computational value. So in today's lecture, what we're going to do is I'm going to give you a standard story for these three families of functions, and then we're going to move to a exciting new geometrical / algebraic unification of them with an overview in mind. Okay, a good place to start is with the circular functions, cosine, sine, tan, and their inverse functions. And here is the usual story that's presented in all first-year calculus courses. There's a unit circle. Typical point on the unit circle supposedly has coordinates cosine theta, sine theta, in terms of an angle theta there. The angle is supposedly measured in so-called radians. And then the dependence on these x and y coordinates on the theta can be expressed with diagrams like this, showing values of, say, cosine x in blue, or sine x in red, or tan x in black. And there's lots of pi's involved, and there's various algebraic relations between all these things. And the whole thing is framed, if we're trying to do things more or less rigorously, usually in terms of some other developments that are secondary or tangential to this geometrical starting point. So in other words, we use power series or integrals, or sometimes infinite products, or sometimes differential equations to define these objects in the first place. But there's serious problems with this entire theory, and in the Math Foundations series I will talk about the many logical difficulties inherent here. But maybe we can focus on just one particular important aspect, which was already enunciated by G.H. Hardy, a very prominent British analyst, around the turn of the century. So in 1908, he wrote a course in pure mathematics, and famously he made this statement: the whole difficulty with regard to circular functions lies in the question, what is the x which occurs in cos x and sine x? And he really pins down that there is some logical problem here with this subject, And we are kind of finessing it a little bit when we rely on the calculator and geometrical intuitions instead of actual real proper definitions of what's going on. So it actually is quite problematic to set this story up correctly, and we're going to have to find an alternative, purely algebraic way of essentially addressing the same kind of issues that the applied mathematicians want solved. Now there's a corresponding picture for the so-called hyperbolic functions, like cosh, sine, tanh, and their inverse functions. And that rests with the relativistic hyperbola, with the equation x squared minus y squared equals 1 that we've already talked quite a lot about. From the standard point of view, we can think about indexing a point on this relativistic hyperbola with coordinates cosh theta and sinh theta. And then the tanh becomes the usual ratio between the sinh and the cosh. And here's kind of the story. There's a point, x coordinate, y coordinate, and then there's a kind of an angle here. But now the nature of this angle is much more in question because it's no longer coinciding with our physical intuition. Nevertheless, we can end up creating pictures of these functions. Cosh looks like this. Sinh looks like this in red, tanh looks something like this. So the same kind of problems that we have in terms of definitions and exactly what's going on in the circular case are manifest here, but they're even more obvious because the geometrical connections are thinner. And in fact, Hardy's question applies here equally. What is the x which occurs in cosh x and sinh x? Do we really have an understanding of what an angle means in this hyperbolic setting? Okay, nevertheless, first-year students are quickly introduced to these kinds of things. Some pictures are drawn, some formulas are expressed, and then we carry on assuming that now we have a foundation. Even though actually, if you actually inquire what's the actual definition, the exact definition of any of these things, then you see that there's a reliance on infinite processes that don't end, and so ultimately you can't compute anything properly. You can rely on the calculator to spit out 10 or 20 decimal places, but you don't really have the objects exactly. So the pure mathematical aspect really recedes out of view. So now when we come to the third family, the log and exp functions, the situation is quite different. And then students are surprised to find that there's some mysterious connection between these functions and the previous hyperbolic and circular functions. So the story is usually presented in the following way, at least in a sort of higher level course, that we start with the standard hyperbola x, y equals 1, and we look at areas underneath that curve, say from 1 to z, maybe z is x, 1 over x, then that region there is what's usually called log of x, all right? But we've seen that this green area is actually the same as this signed area emanating from the origin. So we could also think about log x as being defined in terms of this signed area here. And then that introduces a function log. So if you sort of plot values of the signed area against the x coordinate, then you get some graph that looks like this. And then the inverse graph, the inverse function, is then the exp graph that looks like this. So these are inverse functions in the sense that if s equals log x, then x equals exp of s. And notice that we're not going to use e to the x, we're going to use exp x throughout. So this is the standard story, although in high school courses where these functions are introduced, often there's a different approach taken, and the exp function is introduced first in a also kind of loose, not very precise way, as being somehow analogous to the function 2 to the x or 3 to the x, and having some particular properties that distinguish it from those other ones. And then the log is introduced in terms of the inverse of the exp. So there's a little bit of inconsistency in modern educational circles as to exactly how best to set up these things. And so students are often a little bit confused because maybe in high school they learned one way and then at university they learn a completely different way. Well, I'm going to show you yet another way, okay, which sort of transcends all of these three pictures and elevates the whole theory to a much more insightful level, I think. So for us, the unifying feature of these theories is that they are dependent on the geometry of a central conic. Now, a central conic, by that we mean a conic with a center. What does it mean for a conic to have a center, like this point here? Well, it's such that if you have any point on the conic and you reflect that point in the center, then you get another point on the conic. That's a purely affine notion, because the notion of the midpoint of these 2 points being that is a purely affine notion. So here's another example of a hyperbola. The asymptotes pass through the center, and indeed the reflection of this point and this point is this point. So there's a symmetry about a point, the center of the conic. Now if we put the center, translate things so that the center is at the origin, then the equation of such a central conic is a pleasant quadratic expression. It doesn't have any linear terms then. Something like ax squared plus 2bxy plus cy squared equals some constant d. And notably the parabola, which is very important, but it's not a central conic, so it does not fit into this particular framework that we're discussing. It's got an axis of symmetry, depending on the metrical structure, but it does not have a point symmetry. Okay, so now here we come to the central idea of this lecture, which is a unified view of all these different families of special functions. So the circular, the hyperbolic, and the log exp functions, they all have a common framework. And that common framework is what we could call the log and exp on a central conic. And note that I'm using capital L log and capital E exp here, because I want to separate this a little bit from the usual story. This is a more general, all-embracing picture. And it's all contained in this very simple diagram. So this diagram is well worth studying and thinking about carefully. Here's a central conic, say gamma. And there's the center, say O. And we're going to assume that this center is actually the origin. So we've translated the central conic, so it's centered at the origin. There it is there. And we're going to choose a distinguished point on this conic. And we're going to call that 1. It's like a reference point, or in the context of complex multiplication, that'd be the identity point. But let's just think of it as a distinguished point. And now consider another point on the conic, say Z. Okay, so Z is another point on the conic. Then associated to this situation, we have this region here, formed from the center to 1, center to Z, and the curve itself, giving us this sort of triangular region, but the opposite side is curved, following the curve. Now, this thing here has at least approximately a signed area. We can talk about the signed area in an approximate fashion, at least, for this region. And we're going to call that signed area, say, S. So maybe we could write something like this, the signed area from 1 to Z of gamma. Although this is not exactly the notation we've been using, because there's no parameterization that we're assuming here yet. Okay, so we're kind of taking a bigger picture. But nevertheless, the story is that we have a point 1, which is a reference point. We have a second point on the conic called Z, and associated to these 2 points, we have this approximate signed area S. Okay, that's all what we need to introduce these all-important ideas of the capital L log and the capital E exp. Okay, so we're going to say that S is the capital L log of Z, or we'll just say log Z. The signed area is the log of that point Z. And correspondingly, we're going to say that Z is the capital E exp of S. We'll just say exp of S. So this point Z is the exp of S. So we have these 2 objects. One of them is a number, which is a signed area, and the other one is a point on our central conic. And we're linking these 2, or trying to link them, by introducing these functions that s is log of z and z is exp of s. This is deceptively simple, okay? But it's a very powerful picture that I want to embed in your minds, okay? I don't want you to forget this picture. The relation between a point on a central conic and the corresponding signed area determined by this sort of conic vector from a fixed point 1 to the point z in question. This is how we can introduce the general capital L log function and the general capital Exp function, admittedly in an approximate, a little bit hand-waving fashion now. Okay, this is not an exact definition. This is an orientation to something that we want to establish. Okay, now there are some key properties of these two relations, and they're connected with the Lemmermeyer product on the conic. So I hope that you've watched the previous video where we're talking about log ladders and Lemmermeyer product. So here is our central conic again, and there's the origin, the center, and there's our distinguished point 1. And I remind you that Lemmermeyer tells us how to multiply points on the conic. And it's very simple. So you have a point z on the conic, another point w on the conic. What you do is you connect them with a line, and then you find a line through the fixed point 1, which is parallel to the line through z and w. All right? And now this second line will meet the conic at another point, and that is the product, z times w. Okay? So it's a purely geometrical, very simple and elegant way of introducing a product of points on a central conic once we have fixed a reference point 1. And now in that log ladders video, I explained that essentially the symmetry of the situation, the fact that we could actually multiply correspondingly, at least in the blue, red, and green geometries, gives us some kind of relations. So the relations are the following, that if we take these 2 points z and w, and the product z times w, that the log of zw is the sum of the log of z and the log of w. Okay, what does that mean? So first of all, there are 3 triangle kind of areas here with the curved sides. So log of z will be the signed area of this region here. And when I say signed area, I really mean approximate signed area. We don't have it exactly. Log w will be the signed area of this approximate region from 1 to w and back to the origin. That's the green one. This is the red one. This is the green one. And this relation is telling us that then the corresponding log of zw, which I might picture in blue, okay? So the log of zw will be this signed area. Okay? And the statement is that log of zw equals log of z plus log of w. And the way we can think about that is multiplication by, say, z will send w to zw. And then, so this signed region here will be the same as this signed region here. And so the log of z plus log of w is the same as log of w plus this one here. And by additivity, that's log of zw. And correspondingly, on the exp side, if we sort of unravel this, what it says is that the exp of s plus r is exp of s times exp of r. If s is this signed area here, in other words, log of z, and r is the green one, log of w, okay, then the exp of s is z, and the exp of r is w. So this will be z, and this will be w. And the signed area of this thing here, according to here, is going to be s plus r. So its exp will be z times w, which is the product of exp s times exp r. So these are the 2 fundamental relations for the capital log and the capital X functions in this very general setting. Okay? And they hold sort of for very general reasons. But everything here still has quotes. We haven't defined anything exactly properly here. The objects here are in general only approximate, and there's an approximate aspect to this entire discussion. Okay, so later on in Algebraic Calculus 2, we're going to be looking to see if we can really bring this down to earth in a very concrete algebraic finite way, but that might require some work. So now there are some additional difficulties that lie in store for us if we want to go down this road. So I want to acknowledge these difficulties here. So the first one is really a topological difficulty. And we can see it in the blue situation, where we're talking about the usual unit circle in the blue geometry over the usual complex numbers. So there's our usual unit circle. There's our point 1. Fair enough. There's our point Z. Good. And now we want to talk about the relationship between the point Z and the corresponding signed area. Now, what should that signed area be? Well, it should be the region sort of swept out by the curve as you go from the point 1 to the point Z. And now we can see that there's maybe a bit of a difficulty here. There's an ambiguity because there's more than one way of getting from the point 1 to the point Z. Sure, this is sort of the obvious, fastest way, but it's not the only way. We could also go this way. Or indeed, we could also go this way. We could also go like this, all the way around and then get to Z. Or we could go in this direction 1,000 times and then go back to Z. So those are different ways. And so what are the corresponding signed areas here? Well, one interpretation would be to say, oh, okay, we're going from here to here. Naively, the corresponding log of Z should be the signed area of this quantity, expressed in that direction. But another, perhaps equally possible way, would be to say, oh, no, we want to go in this direction, and so we should be talking about this signed area, where we're sort of proceeding in this direction. So what we're saying here is that the signed area, which is log of Z, is in this context naturally multi-valued. There's not really a single particular value that this log has. There's an ambiguity because of the topological aspect of the circle. Now this is very, very closely connected with a whole bunch of ambiguity relating to the use of angles in mathematics. You will know that when we talk about angles in a circle, there's also exactly the same kind of ambiguity, because if I say what's the angle from this point to this point, well, you can measure that angle in different ways, this way or that way or many times around. And the reason these two things are connected is actually not surprising when you realize that there's actually a close connection between the signed area, S, and the angle, whatever those things are. So in this situation here, I've given you an angle theta. That might be the standard angle that people talk about between this vector here and this vector here. And what's the relationship between this angle and this signed area? Well, at least approximately, the signed area is actually half of the angle. You can see that, for example, let's say we moved our Z to just here at I. In that case, the signed area is going to be 1/4 of the circle, so that's our pi over 4 that we calculated with Leibniz's formula. But on the other hand, the angle is pi over 2. Okay, so in that case, the signed area is actually half of the angle. So the same kind of ambiguities that we have with angles are manifesting themselves here in terms of ambiguities with respect to logs. And I have to also mention that, if we ask ourselves, why do we normalize angles the way we do? Historically, of course, for thousands of years, people used the Babylonian system, where there's 360 degrees in a full turn. And sort of mathematically, the more natural thing to do would be to consider a turn angle of 1 if you go all the way around. But the standard modern approach rests on essentially an arc length. Okay, Okay, so we measure angles these days in terms of arc length around the circumference rather than in terms of area subtended by the rotating radius. Okay, so but if you were starting mathematics and someone gave you this portion of the circle and said, well, how are you going to measure that? Well, one way to measure it would be, yes, to try to measure the circumference length. But another, perhaps equally valid way would be to measure this area inside here. Now the circumference all the way around is 2 pi, the total area is pi, there's a factor of 2 there. And so there's a possible argument to be had about whether we should use the 2 pi as the measure of the whole way around, or we should use pi. What we're doing here when we shift to this log z is we're deciding that question in the favor of pi. We're saying that the areas are more fundamental. That's actually correct, because area is an affine quantity and length is a metrical quantity. Okay, so the affine quantity has precedence, and we've seen throughout this course that it's the signed area which is the fundamental object in the calculus. So it certainly makes sense that we start to think about S as being more important, more primary than our usual notion of angle expressed in radians. So a lot of novel thinking and new kind of thinking required here with these insights. When we go to the red and the green situations, a different kind of difficulty manifests itself, or a different aspect of the difficulty. So here is the red unit circle, there's the green unit circle, there's our point 1, there's a point z, and we're talking about S being the signed area or approximate signed area of this region formed here. So this is all well and good. So log of z makes sense. We have this point z, okay, we can at least approximately get hold of that signed area. But what happens if we consider this point w on the other branch of the hyperbola? Okay, so we cannot continuously go from 1 to w. We can slide along this branch as much as we like. But how do we actually continuously get to there? We can't do that. There's a discontinuity because these are topologically separate. So it's a different kind of topological difficulty that we had in the circle case. But what it means is that if we want to define log of this point w, then we are in a quandary because we don't have a nice region that we can find an approximate area for. It's exactly the same story over here in the green situation. A log of this point z is well defined, at least approximately. It's that approximate area of that thing. But if we have a point w on the other branch, again, it's not at all easy to say how we're even going to think about what the log of this w might be. And maybe that's connected with the difficulty of establishing an angle in these relativistic situations. It's something that physicists have struggled with for 100 years, how to try to bring this natural kind of Euclidean type of geometry into the relativistic story by introducing some kind of angle. And it's always somehow kind of forced. Okay, so, and we can sort of see, perhaps from this point of view, why that is. So this overarching view of a capital L log and capital E exp really encompasses several millennia of work towards circular function tables, hyperbolic function tables, and log and exponential tables. And we can connect it with the geometry of the log ladders in a very nice way to really explain, I think, conceptually at least, sort of what's going on, where we restrict ourselves to maybe domains in which those topological problems are minimized. So here's a picture of the unit circle in the blue story, in the red story, and in the green story. And in each case, I've shown you the point 1 and another point z on the circle, and powers of that point z in the sense of Lemmermeyer, or in the sense of the corresponding complex number arithmetic that underlies each of these geometries. So if here is z, then here is z squared, here is z cubed, z to the fourth, z to the fifth. We could keep on taking powers of z and be rotating around. If we go in the opposite direction, z inverse, z to the minus 2, z to the minus 3, etc., would be going in that direction. Now, if we look at corresponding signed areas, so the signed area from here to here is going to be the same as the signed area from here to here, which is going to be the same as the signed area from here to here. So all of these signed areas are the same. So as we're taking powers of z, we're taking sums of signed areas, or multiples of the same signed area. And here the same kind of situation. There was a point 1. There you see z. Here's z squared, z cubed, z to the 4th, z to the 5th, increasingly faster out. And then corresponding signed areas from the origin. And again, they're all going to be equal. This signed area is going to be equal to this signed area. It's going to be equal to the next signed area, and so on as we go around. And here with this log ladder, with the green geometry, there's 1, there's a point z, there's z squared, z cubed, z to the 4th, increasingly fast in that direction. Or if we go in the other direction, z to the minus 1, z to the minus 2, etc. So here we're talking powers in the green complex number arithmetic. Here there's powers in the red complex number arithmetic. Here there's powers in the blue complex number arithmetic. But all of them are geometrically united by the Lemmermeyer product. In each case, these products are just obtained by the Lemmermeyer construction geometrically. Okay, so now we can look at this very general idea of a log exp table. Okay, so a log exp table is going to relate the signed areas, the s's, and the points on the conic, which are the z's. Okay, so for example, take any one of these pictures, let's say this one here, then corresponding to the points on the conic are the corresponding signed areas. So if we're at the point 1, the signed area is 0. At z, the signed area is s. That's that basic s there. In this case, actually be negative, but that's because the orientation is in this direction. Doesn't matter. And then z squared over there, the signed area of z squared will be the sum of this one and this one, so it'll be 2s. And then the signed area for z cubed will be 3s, and then 4s, and so on. And if we go in the other direction, z to the minus 1 gives us minus s. So this same picture applies to each of these 3 geometries. Each of these 3. And so what we end up having is a uniform understanding of circular trig tables. Circular trig tables are what this thing ends up looking like when we look at things from the point of view of the circle and actually put sort of coordinates on there. Maybe talk in terms of angles or in terms of x and y coordinates. And the hyperbolic situation, hyperbolic trig tables are what happens when you look at this in terms of particular coordinates. Exactly this kind of table. And the log and exp functions, the more familiar ones, are occurring when we look at the same thing from the green point of view. So this unifies the 3 kinds of families of these functions that are important in first-year calculus, and gives us a way of seeing trigonometric tables, both in the circular and the hyperbolic case, and the log and exp tables as all manifestations of really the same ultimate phenomena. So there's much to learn. I'm Noah Wildberger. Thanks for listening.